Hello and welcome back. In this video we will further discuss what enantiomers are, and we'll also discuss how to draw enantiomers and how to name enantiomers. Okay, so we're going to discuss a naming convention called the Ingold-Prelog convention, which labels enantiomers as either R or S. Let's get started. So some stereoisomers can be classified as enantiomers. If they're non-superimposable mirror images, they are enantiomers. Okay, so only chiral compounds can have enantiomers. Let's draw the enantiomer of this molecule. Okay, so if we consider that we have a mirror right here, then we have this chiral carbon, and in front of the chiral carbon we have an ethyl group. So let's draw the ethyl going down and then up, and then here's our chiral carbon. Then moving away we have that methyl going down, and we have the chlorine coming out. So here's our enantiomer. That's one way to draw it. There are several ways to draw the enantiomer. What if we put our mirror plane right here? Then we could flip it over, okay, and we could go down, up, down, and then have the chlorine going this way, okay. And another way to do it is if we put a mirror right in the plane of the board. So I'm going to draw that one, and right behind it we put the molecule, okay. So the main structure, or the line angle formula, would stay in the plane of the board, but instead of coming out, our chlorine would be going back. So if our mirror was in the plane of the board, we could simply swap that chlorine from a wedge to a dash and have the enantiomer. So the easiest way to draw an enantiomer for a molecule is to simply swap the wedges and dashes, and then you have the enantiomer. So in other words, this molecule is the same as this one. If I flip this around, so if I flip this bottom molecule over, okay, and move the ethyl group to the left, then have the methyl on the right, then the chlorine would be coming out. This is where a handheld model would prove extremely helpful. Then this would be the same molecule as this, as is shown in the block. Okay? So the easier way to draw the enantiomer is to invert the wedges and dashes of a chirality center. So we can simply draw the enantiomers by inverting wedges and dashes. So this is the enantiomer of this. This is the enantiomer of this. And what about this compound down here? This is not a chiral compound, so we don't even need to put a wedge or a dash here, because this carbon has two methyl groups attached, making it achiral. What would happen if I flip this molecule on the right over where the OH group is coming out? Now you can see that the methyl groups will still line up with each other. So because we have the same two of the same groups attached to that carbon bearing the OH group, it's not chiral. It's superimposable on its mirror image. A chiral compound must be a non-superimposable mirror image. Let's draw the enantiomer of each of the following compounds. Now these look pretty complex, but drawing the enantiomer is pretty simple, because what we have to do is just swap the wedges and dashes. And we've already been told where that enantiomer is, or I'm sorry, where the chiral center is, because it was put on a wedge. Okay, so all I need to do is take that OH that was on a wedge and put it on a dash. So that's the enantiomer. Now for propanolol, we have this bicyclic system, this fused ring system. Okay. And I just draw the same molecule, didn't I? So what I needed to do was take that OH group and instead of being on a dash, put it on a wedge. So you can draw the exact same molecule, then erase your wedges and dashes and put the opposite. And that's how you draw the enantiomer. Now, because we have enantiomers, we need to give them a unique name. We can't name them the same thing. This is 2-chlorobutane, but one of them is the one enantiomer and the other is the other enantiomer. So what we use is an R and S configuration. Those are abbreviations for the Latin terms rectus and sinister, and we'll see why that is in just a minute. Okay, so we're going to figure out whether our chiral center is R or S so that we can put that out in front of our name and designate the molecule as having an R or S chiral center at a specific carbon. Okay, so using atomic numbers, we're going to prioritize the 4 groups attached to the chirality center. Then we'll arrange the molecule in space so that the lowest priority group faces away from us. And here's where a model kit is going to be extremely useful. Next, count the group priorities 1, 2, 3. So in other words, determine the progression of rotation 1 to 2 to 3 to determine whether the order progresses in a clockwise or counterclockwise direction. Clockwise will be R and counterclockwise will be S. So I know that seems very confusing right now, but let's go ahead and do an example and it should make a little bit more sense. So I've put a little inset of a periodic table down here on the right so that you can see what the atomic numbers are for most of our atoms. Now, the most important atoms that we're going to be using. Now remember, hydrogen is number 1, so I didn't get that in here, but that's pretty easy to remember, okay? So using atomic numbers, prioritize the 4 groups attached to the chirality center. The higher atomic number, the higher the priority. So what are the atomic numbers on these groups? Okay, so hydrogen's number 1. Okay, chlorine is number 17. Okay, carbon is number 6. And oxygen is number 8. Okay, so what is that going to mean? That's going to put chlorine at priority number 1 because it's got the highest atomic number. Okay, oxygen has the second highest, so it's number 2. Carbon has the third highest, so it's number 3. And hydrogen has the fourth highest, so it's number 4. So it's the least, okay? So if you had a handheld model here, what you could do is use your carbon as a black ball. That's usually the black ball that's going to have 4 different holes in it, so you can make an sp3 hybridized carbon. Okay, and most of the time hydrogen is going to be white, so put a white ball for the hydrogen. And usually chlorine or the halogens are going to be green, so put a green ball for the chlorine. Okay, oxygen is usually red, so put a red ball for the oxygen. And then the carbon is usually black, but you can just pick something like blue, put a different ball for the carbon. Now you can take your handheld model, line it up with these connected atoms, and turn it so that your hydrogen is facing away. So our second rule is to turn it, rotate it, so that the hydrogen, the lower priority group, in this case the hydrogen, is facing away from you. Okay? So remember, our oxygen was red. It doesn't really matter what you label the atoms as. You can label them whatever color you want, but in this case our carbon was blue, our hydrogen was white, and our chlorine was green. Okay? So if we rotate that around, that was our 4th priority group was white, right? Our 1st priority group was green. Our third priority group was blue, and our second priority group was red. Okay, now if we flip that around, notice that now the white group is to the back. So if you have a handheld model, now your white is to the back, your green is coming out at you, your blue is now on the right, and your red is now on the left. Okay, so now we can use that information to determine the progression of rotation. So the progression of rotation is 1 to 2 to 3. This is actually counterclockwise. And the Latin word for counterclockwise would be sinister. Okay, and so we say this as the S configuration. If a molecule has the progression of rotation counterclockwise, it's S, and so we just determined that this molecule has the S configuration. Now notice it looks like 1 to 2 to 3 here, but our fourth priority group has to be pointing away in order to do this determination. So this molecule is S. Sometimes we have a lot of the same groups attached, and it could be very tricky to determine whether the molecule is R or S. As in this case, we'll have to keep moving away until we get a tiebreaker. So let me give you an example. So for this chiral center here on the left, we have an OH and a hydrogen attached, and that's not a problem. But here we have carbon and carbon. So we have two of the same atom. So if we consider atomic number, oxygen is going to be number 1, hydrogen is going to be number 4, but then carbon versus carbon, we can't determine that. So what we're going to do is move away until we find the first point of difference, moving away from that chiral center until we find the first point of difference, and that will be our tiebreaker. Okay, so we're going to move away until we get a tiebreaker. So as we move away, we have carbon versus carbon. Each of those carbons has 2 hydrogens attached. Okay, so as we move away, we have carbon, hydrogen, hydrogen. So make a little chart and put the higher priority group on top. So you don't add the atomic numbers together, you put the higher priority atom on top, and once you find a higher priority atom, you've got a tiebreaker. Okay, so then we're going to move away again to this carbon versus this carbon. Okay, so now we have, as you can see here on the right, this carbon has carbon, hydrogen, hydrogen attached to it, and this carbon has carbon, carbon, hydrogen. Okay, so I've got carbon, hydrogen, hydrogen versus carbon, carbon, hydrogen. Okay, so we've got a carbon, hydrogen, hydrogen versus carbon, carbon, hydrogen. Alright, so we found our first point of difference. This carbon, carbon, hydrogen is going to trump carbon, hydrogen, hydrogen, and therefore the right side is going to be higher priority than the left. Okay, so this is actually still a little bit difficult because we have our higher priority group, our lower priority group coming out at us, higher priority group going away. So we've got to flip this molecule over to determine whether it's R or S, okay? And we don't have that done for us. So let me flip this molecule over. So we have the isopropyl group, then we have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And 3 carbons away from the isopropyl. We've got the OH group is now coming out, and the hydrogen is going back. Okay, so let's prioritize these guys. That's going to be 4, 1, 2, 3. Okay, progression of rotation is 1 to 2 to 3. So that chiral center is R. Alright, so here's another example of this. Our chiral center is here. We're going to analyze all of the groups attached. So we've got oxygen, hydrogen, carbon, carbon. Oxygen and hydrogen we can prioritize right away. That's priority number 1 versus 4. And now we have carbon versus carbon. That's a tie. So we look at what's attached to those carbons. Okay. This carbon on the right has carbon, carbon, carbon attached. This carbon on the left has oxygen, hydrogen, hydrogen attached. Okay, so oxygen trumps carbon, so that makes that group on the left number 2 versus the one on the right, which is number 3. Alright, and if you have, oh, did we do R versus S here? We did not. Okay, so what are we going to do? Again, our hydrogen's coming out at us, so we've got to flip this molecule over, which is much easier if you have a model kit. Let's go ahead and flip it over. Now our hydrogen's going to be going back. Our OH is coming out, okay? And so that's going to be 1, let's get a different color, 1, 4, okay? 2, 3. Okay, so 1 to 2 to 3 is our progression of rotation. So that makes this R. Configuration is R. So we could have determined that without flipping it over if we'd said 1 to 2 to 3 is S, but we know that since our lower priority group is coming out, we have to reverse that. Okay, so it looks like S, but since the lower priority group is coming out, we know that it has to be R. When prioritizing for the Kahn-Ingold Prelog system, double bonds count like single bonds, so this would be as though this carbon was attached to 2 oxygens. Now remember, that's not a chiral center. Our chiral center is here. So we have to determine what the priority is, what the designation is of this carbon, right? And so how are we going to do that? We're going to move away until we find the first point of difference. So this one's pretty tricky. We have carbon, 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 carbon. So we've got a 4-way tie. So we've got to break that tie. Okay, so let's go ahead and do this. Alright, so our chiral center is here. And we got to prioritize everything. So we're going to move away until we find the first point of difference. Moving this way, this carbon has hydrogen, hydrogen, hydrogen. Okay? Moving this way, this carbon has the carbon that's attached over here, plus hydrogen, hydrogen. So that's carbon, hydrogen, hydrogen. Moving this way, okay, this carbon has this carbon moving this way, plus hydrogen, hydrogen. Okay, so I've got carbon, hydrogen, hydrogen. Okay, so these two are tied. Moving this way, this carbon has oxygen, oxygen, hydrogen. Okay, so at those 4 points, I can do 2 priorities. This is priority number 1. This is priority number 4. Now I've got to move away until I find the first point of difference. So moving away, this carbon has hydrogen, hydrogen, hydrogen. Okay, moving away, this carbon has carbon, hydrogen, hydrogen. So this is going to be priority number 2, and this one's going to be number 3. Okay, so let's redraw our molecule here because this looks just too junky. Alright, so I've got done, done, done. Okay, so here's our molecule, and we've prioritized everything. Let's go ahead and write it out. So this carbon was priority number 1 because it had the oxygens. This one was number 4. This one's number 2. And this one's number 3. So again, we have our priority number 4 coming out at us. The progression of rotation appears to be 1 to 2 to 3. Okay, so it looks like R, but since the lower priority group is coming out, this configuration is S. Here's another trick. If you switch two groups on a chiral center, you've just created the opposite configuration. So if you want to convert R to S, just switch two groups. So you can use a trick to adjust the molecule so that the lowest priority group faces away. In other words, you can just do like I just said. Pretend that the lower, you can just use the priority of the groups as they are, but if the lower priority group is pointing towards you, then just reverse what you have. Okay. So here are our steps. Identify the 4 atoms directly attached to the chirality center. Assign a priority to each atom by atomic number. If they have the same atomic number, move away until you find the first point of difference. Rotate the molecule so that the 4th priority group is on a dash, pointing away from you, and determine the sequence 1 to 2 to 3, whether it follows a clockwise or counterclockwise order. So let's assign the configuration of the chiral center in the following compound, okay? So where's our chiral center? It's right here. It's already got the dash for us. So that means we have a hydrogen coming out, because apparently the author of these slides didn't want to make anything easy. Okay, so that's going to be number 4. Nitrogen is number 7 here, okay? So we have hydrogen, nitrogen, carbon, carbon. So with that first layer, we've got hydrogen, nitrogen, carbon, carbon. Nitrogen is higher than carbon, so this is going to be number 1. Okay, then we've got carbon versus carbon, so we've got to, at that layer, we've got to determine how to break this tie. This carbon has carbon going that way, hydrogen, hydrogen. This carbon has 2 oxygens this way because that double bond counts twice, plus another oxygen. So we've got carbon, hydrogen, hydrogen versus oxygen, oxygen, oxygen. Oxygen is higher than carbon, so this is going to be priority number 2. Priority number 3, okay? The progression of rotation looks like 1 to 2 to 3, but since the hydrogen is coming out at us, which is the lowest priority group, we reverse. So it looks like R, but since it's the hydrogen's coming out, this is actually S. So if we flip this molecule over where the hydrogen's going away, we would see that this is actually S. So let's see if we can determine the R or S on all of these, okay? So this top molecule up here, we've got 4, we've got 1, okay, we've got carbon versus carbon. This carbon on the left has hydrogen, hydrogen, hydrogen. This carbon on the right has carbon, hydrogen, hydrogen. Okay, so that is priority number 2 versus 3. Okay, that's 1 to 2 to 3. The hydrogen's going away from this, so that is R. This molecule on the right has a chiral center here. I've got fluorine, which is number 9. Hydrogen, which is number 1, so that's going to be priority number 1, priority number 4. Then I've got carbon versus carbon. The carbon at the top has carbon, carbon, hydrogen, because these carbons on the double bond count twice. The carbon at the bottom has carbon, hydrogen, hydrogen, so that's carbon, hydrogen, hydrogen. So then we have priority number 2 versus 3, okay? So this is 1 to 2 to 3. Hydrogen's going away, so this is S. Alright, the next molecule has two chiral centers, so let's determine each one. The one on the left has hydrogen, oxygen, carbon, carbon, so that's going to be 4, 1, and then we have to break a tie. So carbon versus carbon. Carbon on the left has carbon, carbon, carbon. Carbon on the right has nitrogen going this way, carbon going this way, and then a hydrogen going back. So nitrogen, carbon, hydrogen. Nitrogen trumps carbon, okay? So that's going to make this carbon here priority number 2 and this one priority number 3. So 1 to 2 to 3, this one on the left is R. Okay? And I'm going to have to either erase this or redraw the molecule. I think I'll just redraw this molecule. Okay, so now I'm looking at this chiral center right here. I need to determine its configuration because the one on the left we determined was R, right? Alright, so that carbon has nitrogen, so that's going to be number 1. Hydrogen is number 4. And then we have carbon versus carbon. Alright, this carbon at the bottom has hydrogen, hydrogen, hydrogen attached. The carbon on the left has oxygen, then carbon this way, then hydrogen that way. Okay, oxygen trumps hydrogen, so that makes this number 2 and this one number 3. Okay, hydrogen's going away from us. The progression of rotation is 1 to 2 to 3, so this is S. Alright, one more molecule here that has two chiral centers. The one on the left is chlorine versus bromine. Okay, and we have fluorine, chlorine, bromine, iodine. So bromine is going to be higher than chlorine. Remember, that's bromine then iodine, right? So, but actually, this carbon, and what does it have attached? It has chlorine, carbon, carbon, carbon. So that chlorine is actually number 1. Okay? Now, as we move away, we're moving away in layers to find the first point of difference. The next carbons, we got carbon, 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 we got to find out what they got attached to them. So this carbon up here has bromine, hydrogen, hydrogen. Okay? Bromine, hydrogen, hydrogen. This carbon over here has chlorine, carbon, carbon, because carbon going that way, carbon going that way, that carbon counts twice, right? So this carbon here has carbon, hydrogen, hydrogen attached to it. So we've got bromine versus chlorine versus carbon. Okay, so the bromine is going to be the carbon bearing the bromine is going to be priority number 2. The carbon bearing the chlorine is going to be number 3. Okay, the carbon with just a carbon attached at that point is going to be number 4. Now this is difficult because we don't have it coming out or going away. The lower priority group is in the plane of the board. So let's pretend that our eye is over here and we're looking that way. Okay, down this carbon. So that means coming out we've got a 1, and then we've got 2 and 3 going counterclockwise. If you don't believe me, make a model of this. So that molecule is S. That goes counterclockwise. Let's draw the molecule again. To get that second chiral center. Okay, next chiral center. We've got at this chiral center, be as quite as bad on this side, right? We've got hydrogen, that's number 4. Bromine is number 1. Then we've got carbon versus carbon. Carbon on the right has got chlorine, carbon, carbon. The carbon on the left has carbon going that way, then hydrogen, hydrogen. So this group is going to be number 2, and this group is going to be number 3. Okay, it looks like 1 to 2 to 3. It looks like S, but since the hydrogen is coming out at us, the 4th priority group is coming out, this is actually R. Okay, so this molecule has S. This on the left is S, and on the right is R. So how do we use this? We use this to distinguish the molecule from other molecules by its name. So on the left we have R2-butanol, and on the right we have S2-butanol. So we put the R or S out in front of the name in parentheses. If we have more than one chiral center, we put the number in front of the R or S. So it's the case on the bottom. We've got 3-methyl-2-pentanol. So at the second carbon we've got R, and at the third carbon we've got S. So that's 2R, 3S, 3-methyl-2-pentanol. So remember, the parts of a name of an organic molecule are parent, unsaturation, functional group, okay, and then out in front we've got substituents and stereochemistry. So stereochemistry always goes in front. Alright, thank you for watching. Practice with your model kits, and I'll see you next time.